Okay. Yeah, so what's the math version? So like if a conjecture is solved by Mark, then it's just a theorem. So otherwise, yeah, okay. I complete the math version of.
Excellent.
All right. So now let's start talk about some math. So probably you all know that I have been working on network coding conjecture for a while, right? But I have not formally talk about it anywhere. So now I have a chance to. So now we're coding here. Yeah. Yeah. So this will be a lecture 0, and which I will give a introduction to network coding theory. And if you are interested, then you are welcome to our reading group this semester, which happens every Tuesday noon. And so today I will try to introduce two topics. One is network coding conjecture, which will take the first half of the talk, and the second half I want to convince you that this field is broad and it's connected to other things like multi-party computation, distributed computing. By giving several results actually very recent, one in 2023 by Marab Badr, which actually like asks very basic questions like what is the millionaire's problem, questions on the not the computer graph, right? On this graph, and what things you can do. Yeah, so anyway, let's first start with the section. So yeah, consider you have a graph sheet. So under and a set of sourcing pairs. So you have a sourcing pairs as I T and now the conjecture asks a very common problem that can you do information flow better than multi-commodity flow? Say, okay, now I probably need to give you some background on graph, like what is the formal definition of multi-commodity flow. But kind of idea is, if you are not treating the information as physical commodity, can you do better? That can you use like coding tricks to increase the throughput? So high level, you can think about the capacity of the edges is the upper bound on the entropy of the variable you send through the edge, right? So that's the analog of like how you send information on a graph. So in general, the graph can be variable. Yep. So, and the conjecture says in this specific problem called multiple unicast, that you have a set of sourcing pairs, you cannot do that physical commodity flow is the best you can do. And it remains open for 2 days. Okay. So, okay, conjecture. It's known by several names. One called B and D's conjecture, or multiple unicast conjecture. Says coding rate equals to multi-commodity. Right, and yeah, before I formally introduce say the network coding, let me motivate this a little bit more. By connecting this to a very fundamental math problem called integer multiplication, that's that kids learn how to do it in quadratic time in primary school. So integer multiplication is you are given two yeah, probably that equals x y. Yeah. So let's say they are binary, right? And you want to compute x times y. So this actually has a long story. So before 1960s, actually people only know quadratic time algorithm. And common graph in 1960s. So I don't know if I spelled it correctly, but like the very famous common graph, he set up a seminar saying, okay, let's prove the time bound of this. Okay, he believed that we actually need quadratic time. And then, like in the seminar, just after a week, his students like gave a better algorithm, something like the log this, something like 5.8, if I remember correctly. Yeah, just within a week. Right, and yeah, and since then, like people know actually you can do better, right? Like people have better speed. The very fast one runs in log and time. And I forgot the year. But then there are follow-up work in improving this. One famous work is by Haeupler in stock 2007. So we can do this in this is some big improvement, and actually very recent. Harvey and Corbin, but log and very like this is a very clean upper bound for the long and low part. So yeah, so now we are doing the same thing as common graph. We want to prove this in time. And in 2019, like actually people shows condition on that conjecture. This is time. Yeah, but you need condition on the network coding conjecture. Right? Yeah. Yes, and this so today I will prove this. Yeah, this is actually very simple, like application.
You know what the constants are like? Because it's very difficult. Which one? The constants were you in
I don't know. Okay, let me talk a little bit more on this. So they prove like for general F you do you can do it in n log q log n times log q. So yeah, but for constant I don't know. This is just for people care more about scientific. Okay. Yeah. So now let's prove the theorem. Um, Probably let me. I cannot see my notes because my computer is recording. Let me try. um. Okay. So actually, they proved something even stronger. That they proved this lower bound for not only integer multiplication but also shifting problem. That you're given x in what and L in and the output is a y that shift x by L position index, right? That you does this make sense? Right, it's shift shifting function.
Can you give an example?
Hmm?
Can you see an example for what they always do?
Sorry.
An example.
Example of shifting, yeah. So let's say n equals to 3 and x is 1, 0, 1, and L is 1. Then you shift it to left by 1 position. It outputs 0, 0, 1, 0, 1, 0. And you shift 1, 1, 1 to left by 1 place. So this is a simpler problem than multiplication because it's only multiplied by like 2 to the I.
Why is it doing? Like, why is it sort of do?
Yeah, you can define it like you can align them, but anyway. Yeah. Okay, let's prove this. So let me formally state the theorem. Assume any let me see. Um, that's, uh, uh, that size. Uh, so let's consider any for every j. I want to say the size of indexes.
Sorry, will you define what is network conjecture, network coding conjecture formally, or?
I think this to prove this theorem, you don't need a formal definition. Like formal definition, it's painful. Like you need to define entropy, whatever, a lot of things, right?
So you don't need.
But you will see. This proof actually, I want to show this proof because I want you to have a flavor on the network coding conjecture without formally. Yeah. So let me use of L. So okay, the proof is the following logic. So assume you have a proof back. Okay, let's consider arbitrary circuit C. Let's compute this function. And then you consider for any index J, the set of shifting variable L such that the distance on this circuit, the graph induced by this circuit from xj to yj plus L, is at least 0, 0, 1, 0, 1, 0. 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0 say, let's say half. So you come, so we want to lower bound the size of this thing.
What is 2C?
So 2C, I set it as 2C because the degree of each vertex in the circuit is at most 2C. Okay. C is a constant finite question. So let's say this constant is.
What is VC?
So this is on the circuit induced graph, the distance from xj to yj capital. Like the distance on the graph. Yeah, say the undirected graph induced by circuits. Right. And what is the size of this set? So this, I think this is at least minus square root and probably some constant. There might be like constant 1 or 2, but this. So why? Because with this step, right? So each step the size of the set multiplied by the most 2C, right? So the number of vertices you reach within this distance, yeah, is at most the square root n. So the number of vertices remaining is at least minus 1. Does this make sense? Okay. And now, just using probability method as the probability that you choose L in N, that at least half of J is far from this destination. It achieves non-zero probability. So I selected L uniformly in the set N. And what is the probability that at least half of index J, it is that far from its destination. So this probability is positive, right? So formally, say no. So now it's J. Like this. So what can show this? Yeah. So now let's consider the communication problem. So like peak. So peak such. Okay, now let's consider the communication problem that you shift x by a star in this circuit. It actually takes the flow problem should take a log n at least, right? You consider now that's other, yeah, it's just a one step further. So this so peak such L I'll show the capacity C is actually so this is a flow, the J is flow on E, and Yeah, I think this thing is at least a log for that this is fraction of j. Okay, so the let's say every edge has capacity 1, right? Like in this problem, let's say each um, each edge has a capacity 1, right? Like it's let's say the gate if it has multiple outputs split into multiple edges. And now the capacity E, like you have the flow constraint that all these J flows share the capacity of the edge, right? This is the definition of multi-commodity flow, right? And then you switch the summation. And what about this? This you use the lemma we proved, right? So that's because you send from xj to yj plus l, this bit, right? Yj plus will need to know xj. Yeah, so you actually you use the here is a step. Okay, this might be too fast. Yeah, let me break it down a little bit. So this uses network coding conjecture. Oh wait, this doesn't. So inherently it used this way. So because the circuit computes the integer multiplication, and by network coding conjecture, you have a multi-commodity flow, right? Like sending from each xj to yj plus l, right? And here we already have the assumption that there is such multi-commodity flow, and we can lower bound the size of E. Yeah, this is the fact. This is by the fact that you prove the distance of the source and sink. Then any path in the flow need to take at least half of log n. That log. So then summation over all these fractional paths, you have like at least half n of j's. You have this thing at least half log n. So you have omega n log n. So any question?
Explain the figure of what to have all two students.
Sorry.
You explained the last one.
This step. This step.
All two students.
Yeah. So okay, probably I need to define a little bit of multi-commodity flow. Yeah. So it's given a graph and set of terminal pairs. A multi-commodity flow is like I assume everyone knows max flow, like single commodity. Like ST, the single commodity flow is graph with a sourcing pair, and you have a flow from S to T, such that for each vertex, the inflow equals to the outflow, and you want to maximize the flow, say, sent from S or like received by T.
The flow you always assume as gets 1 unit.
So let's say this is unweighted graph, then every edge is like 1. Is 1. But now since there are multiple demand pairs, there are k of them, so they share the capacity of the edges. Right? So we have a constraint that for any and E, the summation of J in K. Let's say use that notation J in K, then FJE is at least the capacity of E. Or like in this problem, K equals to N and the C equals to 1. Right? And then for any J, if you only look at the flow itself, it should satisfy the E equals to all constraints, right, on every node that you are sending. Actually, sending whatever you received out, right? So this is the flow problem. And here, to answer your question, why the total flow on every edge, if you look at the flow of J, the total flow should be at least this, because for each flow, there's a theorem that you can always split into fractional paths, right? Fractional paths. So each flow is one way of seeing it is using this LP constraint that E equals to out, right, whatever. And the other way is to split the flow into paths, right? Given a flow Fj, you can split into paths. So another way of doing it is split in PST. So the flow of the path. Okay, this I probably need to assume some background on next flow. Yeah, the questions are welcome.
Sum of E in the Fj is at least half 2C log n. How do you say that? Because half 2C log n is a distance between input and output, right? How do you convert distance into that? You don't know.
Yeah, so this uses a path decomposition theorem. That's because for each path, the distance is at least that much. And the summation of the fraction of the paths should equal to 1, right? And each of them have that distance, so it requires that much input.
And how does that the coding concept?
Yeah, so this I would say this whole thing use network coding conjecture in the very beginning, actually, that you need to assume that there exists such multi-commodity flow, right? There exists such multi-commodity flow that achieves throughput, which you use network coding conjecture because you are assuming that this circuit actually computes the integer multiplication, that each yj plus l knows xj. And by the conjecture, you turn it into a multi-commodity flow.
What do you mean by no? Say,
So you assume circuit C computes this shifting problem.
right.
Yeah, and then by the network coding conjecture. Okay, so what does this mean? If we fix L star, then by this conjecture, there should exist flow from each xj to yj plus L star.
Either existing of flow, you mean there existing of flow.
A multi-commodity flow
Value non-zero.
of value what? What value exactly what? Yeah.
Why?
Because the coding rate is 1. So the coding rate means if you have okay, say so you formally define like so for each source, so this is Ahlswede, this is TJ, and the demand are unique because you are just sending one Boolean variable, which has entropy 1. And you are assuming there exists such a circuit. Actually
So the coding,
achieves this.
so the coding rate means like the variable yxj and yj plus L star are the same. Like either then.
So you send this variable here, right?
I see.
Yeah.
I see.
And the multi-commodity flow means you send like one physical commodity from xj to yj plus L star.
Why do you assume constant and not know?
Yeah, that's something you require in this proof. Otherwise, you cannot work on this. Because some simple graphs might have the distance constant, like with like linear family knot, right?
But that graph might also compute faster than that log.
Yeah. So this theorem only holds for constant finding out. But if even this, I don't think complexity. I think they care even this a lot. This assumption. Okay, so this is the first half. Yeah, thanks for questions. Clarify things. Shall I move on?
It's still saying that y that's bigger than half.
Yes, so so you achieve throughput 1.
Right.
And by the path decomposition theorem, so for any flow, you can always, so the flow value of J, let's use say L3. It should equal to path decomposition of this. So for flow, what does path decomposition means? It means like you decompose it into several paths. Yeah, that's such that like they uses the edge capacity assigned to this flow. And this means you can always do this path decomposition. And this, let's say there's a fraction, right? Let's say RP. And now you can see the distance, like the length of the path, the length of P is always at least a half log n. Right? Then what is the total like the volume of the flow J? Then it should be at least the volume J. I call this volume J. Should be at least summation RP times LP, right? This is by path decomposition. And this thing sums up to this. Okay, this equals this is the definition of sorry for this. So but the summation of RP equals to 1. So this is by our assumption. So this volume is at least so this thing, right? You say this LP, you see this is like this, and the summation of RP equals to 1, then this is that the volume is at least.
But why is that small? The summation FJ, the like if you are counting the summation of all the flows along the edge, why is that?
Oh, I just define it as volume, and I say, so do you agree with this? I just define this quantity as volume.
You're saying this is not.
As that one. Do you agree with this? The volume is at least summation RP. Like you use path decomposition, then it is at least
Okay, so.
So say
So,
okay.
for example, so here's another example in my head. This but what am I missing? So let's say this is one path, like the outside flow.
The flow of J is just one path,
Right.
yes.
Right, and the summation of FJ always is the.
I use summation on every edge, right? So it equals to the length of the path times the the fraction of this path. Okay. Cool. So so now let's switch to a very different context. So again, given a graph undirected, and now let's consider multi-party computation. So insecure model, right? What if there have that the Eve controls at most F vertices? Right. What can I do? So we want to ask, can we jointly compute some function such that if there's nothing about the I think this for this setting Yashin knows better than me. Function probably also knows better than me. So please correct me if I say something wrong. So let's assume F is okay. That's not an assumption, but so each vertex they have a input, right? That's one xn. They want to jointly compute some function g, right? So you want if know nothing besides theorem. Is that correct? Yes. Yes, okay. Okay, so then what's the assumption? So I think in multi-party computation, it assumes a graph to be a complete graph, that each pair of vertex they have a secret channel. And in that case, one can do if f is not a majority, like f is less than half of the set of the graph. And here, this is a result by Parter in Fox 23. So it says once we have vertex connectivity at least, then you need to do some logarithmic factor. Then you can do this. And even more, she showed that you can complete the sublinear rounds. Formally, it says let's consider the billionaire's problem that each vertex wants to know who is the richest among its neighbor. Then it requires poly f times let's do an informal version SQG. Okay, I don't think I will introduce what SQG is in this talk, but you can think like for good graphs like the expander graph, this is the polynomial, and for I think this gives intuition that you can do sublinear round.
What's this one?
So this number.
What is the? Yes, the order of what is this order?
Yeah, the vertex connectivity means the number of vertices. There's the least number of vertices you remove from the graph to make it disconnected.
So and what is the other one?
Okay, let's just lay up login.
rounds.
And this is round, the number of rounds. Like each round you can talk to your neighbors. Like formally, this is defined as congested model, so one can do that. Right. So this is quite surprising. So I will not show you this theorem, which is a lot of pain by using graph and algorithm hammers and by applying, say, one particle for multi-party computation of the black box way. And
Sorry, I have a not super related question. But I'm not very familiar with this multi-computation literature. These results, are they, even if you consider Eve having like maybe some distributional knowledge, or if Eve is doing some like learning over a multi-round like game, are these results still holding that like she can't learn anything, even like a probabilistic like answer for what she's trying to find out?
So I think for this problem, this is considered the information theoretical way, right? Like you just control these vertices. They even still needs to follow the protocol. That is not like learning or something. You just have unbounded computational power. Right? So this is like information is theoretically it still learns nothing about the input of others, whatever functions of that. But yeah, question. So I think today I only have time to prove like a very baby step of this, but I still think that's already some magic. So let's consider a very simple. It uses a lot of network coding. I will show you a baby step, which actually takes.
It doesn't use the conjecture.
Doesn't this is not related to the conjecture. So this is, but this you can think about this. They worked on the same problem, but in a different set, like in F secure set. So in a partial step, Marav's, she actually need to solve multiple unicasts. The problem might be fine for network coding in a secure way, but not that problem. Yeah. So let's think about this baby step. So you have G and say now there's only one sourcing, like S want to talk to T. Say just sending one bit. Yeah. And what is a necessary and sufficient condition that Eve learns nothing? So let me just tell you, I don't have time. So G need vertex connectivity at least F plus 1. So if it has, so you can see that one direction is easy. So let's start with T. Say
Percent are only SNT.
so this S and T are two vertices in graph, right? Like S1 to talk to T. So each round, by the definition of congest, you can talk to your neighbor. Yeah. So it's undirected, like both ways. The U and V, they can talk to each other. And the vertex connectivity, once it has plus 1, you can show actually one can finish in round of diameter D. So D is the diameter of the graph. Means the diameter of the graph is the first the like two vertices furthest to each other, the distance of. So I would say this is already some interesting result because this doesn't depend on what are the f edges you listen to. This is a universal protocol, and it also so actually when I first look at this theorem, I guess this answer should be something like the diameter of G minus F, right? You need to send through some safe path, but actually it achieves around D. So I think I need 10 minutes. Okay, so do any of you want to have a try?
Give us a view.
Huh?
Give us the view.
I guess like you sort of.
Yeah, so I think one thing for the network coding field, like very general hint is when you XOR bits, magic happens. Is that a hint? Okay, I think yeah, you will see this trick like throughout the reading book. So the way of doing this is you take from T a BFS tree, right? And the height of this tree is almost D, right? And now of course there are some off tree edges. There are some off tree edges like this. I might need to use other colors, but there is only white. Okay, let me use Dashman. So and now you want to do a bottom-up collection of this information. So you do it in like say let's say this is H. You do it in like H plus 1 round. How for each off tree edge, you first generate a random bit here, like for both directions, the same random bit. Okay. And the idea is we want to XOR them like in the bottom up way that they eventually meet in the rule that they cancel out. So I want to send from S to T a bit, but the information theoretically, the if controls at most that. Okay, this is edge connectivity. Okay, sorry about this. So now we think the if control that most have right. So I want to the trick is that I want to generate a random bit. So of course the protocol needs to be randomized. such that it follows the eavesdropper. That's whenever if it doesn't cut the graph, there are some randomness it doesn't learn, and you are explore things together. It only learns a linear combination. So that's a high level idea, right? And by along doing this, you just do a special thing at the source x. That's as XOR the input bit into its message and send it up to its parents. Okay. So this is formally. So in the first row, each off tree edge send a random bit in both directions, and then you just collect the information bottom by just XOR things, XOR all the input of its true at every node, and you do each round. That's it. Does this make sense? Okay, I actually completed the proof in 5 minutes. The proof is, yeah, but this is actually a baby step of that. Like it takes that's okay. Yeah. Probably let me tell you something more. Like you can actually do broadcast in broadcast in some linear routes. Yeah, like secure. This is again universal, like the same setting of that, right? And multiple unicasts, but related to the quantity SQ. And with all these building blocks and some more technique, like Moran finally achieves this. Plus, like actually in this paper, it's actually solving a very general problem called compile. That given any distributed algorithm, there is a compile that compiles the algorithm such that it achieves information theoretical secure. Like it works for arbitrary things. So the billionaire's problem is just the sign.
So the nice thing about Powerzoll is that the number of rounds is very small.
Yes, and it's not obvious, like even at the first glance, that you can achieve information theoretically secure. But like this is even more magic. Like this, it's just like this result. Like this itself is a paper in 2004, and this people actually found like okay, this problem actually achieves the round complexity, and that's the same. Right? Like there are like 2 for the results.
Is there any overlap with the
Okay, so yeah, this so this is so one of this is at least skewed. If you want to achieve universally, yeah.
And this is for the millionaire problem.
Yeah. For arbitrary problem, there is I think there is a project. So this is a blow up that and also there is a delta square that related to the max degree of the graph. So it's for the general compiler. There are several more factors there, but the idea is it can always achieve something almost optimal. Like in good behavior graphs. Okay, yeah. So yeah, I hope you like that coding.
Why isn't it called coding?
I don't believe that.
You don't